How you doing, everybody? My name is Duncan. I work for Typesafe, and I'm an engineer. I work on monitoring, but today we're going to talk about something a little bit different, Akka persistence and eventual consistency, and distributed systems in general. And this is a pattern, I think, which can be very useful. And as we build systems and as we reason about really two primary areas, an area called identity and an area called state, both of which can be challenging in a distributed system. So for our outline here, we have a lot to cover, and I'm going to go through it relatively quickly because of the time constraints, but I believe from that you'll be able to pull some things to at least, if you're not familiar with these concepts, to dig into them a little further to see if they're of use to you. So let's get started. One of the challenges that we're facing is the reality of the context in which we design systems has changed in the last 30 years. It's become much more larger in view. The volume of data that we have to deal with has increased beyond even 10 years ago what we would have ever dreamed of, and so forth. And it's introduced all kinds of new variables that we have to account for. And the result of that fact has led us into a slide which I have shamelessly stolen from one of my coworkers, Jonas. But the idea is we had, in yesteryear, we had the notion of single machines. Today we have clusters of machines. We had single core processors. Today we have multi-core processors. We had expensive RAM. Now we have cheap RAM. And all these technological advancements have come on the scene in the last 10 to 15 years. And we need to utilize them to their extent. We need to use the entire system. Expensive disk, cheap disk. I remember when I had my first computer, I paid $300 or $400 for, I think, a megabyte of disk space, or 2 megabytes. Now you can get a terabyte for that price. So the change is incredible. Slow networks, fast networks. Network latency is one of the key things in distributed networks. Few concurrent users, lots of concurrent users. Just 15 years ago, I built a system that had, I think, 5,000 or 6,000 users. That was considered to be rather large at the time. Recently, I talked to a client that was looking at 3 to 10 million concurrent users. So quite an increase. Small data sets, large data sets. Large data sets are becoming so large that the data is really an exercise of reducing the noise or eliminating the noise so you can get to what is valuable into the covers. I heard once said that people that are effective or people that are successful have one trait which is very important, and that is that they're able to accept criticism. And they take criticism and they look at it as a gift, and they look at it as a jewel encased inside of something like coal, and they crack away the things that are useless, and they mine out of that the gift which is in, which is what the criticism was intent for. So it's the same thing with large data. The noise is so great you have to mine out the true meaning from all the excess noise. And latency. Latency in seconds is now milliseconds. You have the notion of real-time and near real-time data. And so my underlying message, implicit message if you wish, is that this is much deeper than we might think. It's beyond just coding. It touches to our everyday lives, if you will. MIT Sloan Business School of Management and Capgemini did a review in 2013, and they basically said that companies that do not embrace this type of change, and I don't mean event sourcing particularly, but the change in how distributed applications are making a huge impact, face what they call a digital imperative. And if they don't embrace this, then they can face technical obsolescence or competitive obsolescence. And I think the canonical example is Netflix versus Blockbuster, right? A company that started out that was the king of video and then is no longer in existence because they waited too long. And unfortunately, that has an impact on us, right? The people who give us the money that we use to feed ourselves and pay our rents and mortgages and all these types of things, that trickle-down type concept, will eventually come and affect us as well. So it's an important thing, a very important thing that we have to consider, that the work that we're doing and the way that we reason about building applications and solving problems has a much deeper impact than we may realize. And this quote out of our book, basically, the demand for these types of solutions underlying being distributed has exploded, and it's in response to customers, right? They want immediate response, no failure, access anywhere, the whole Internet of Things, if you're familiar with it, which I'm sure you are. And I'm in the camp of believing that one of the primary and main ways to solve this problem is distributed computing. In fact, I go so far as saying only. But I think it's extremely important. So at Typesafe, we have the reactive view of things. It's the reactive manifesto, if you will. You see at the bottom, message-driven. It has an arrow that points up, and then two arrows that kind of circle up. It's kind of like the base, of which two pillars are resilience and elasticity. And agreeing with Jonas, resilience is foundational to the support of this entire thing as well. And then ultimately leading to the goal, which is to be responsive. In light of failure, in light of increased load, I am going to respond to you. If I'm speaking to somebody and I ask them to do something for me, and they do not respond to me, I don't know what they're doing. I don't know if they're dead. I don't know if they're alive. I don't know if they heard what I said. But if they say, hey, I can't do that right now, but I can do it in 5 minutes, I'm happy. They responded to me. So the customer wants responsiveness, and they expect you to be fault tolerant or resilient and be able to handle increased load. So again, kind of a strong statement, but I believe that modern applications need to embrace this type of thinking, incorporating this type of behavior into their DNA, right? To really kind of think outside the box and not just learn it, but to kind of live it. You can use the term religion if you want, however you would like to define it, but I believe it's very important. And one of the tools in achieving this, I believe, is very useful, is something called event sourcing. So what is event sourcing? Historically, I'd say the last 20, 25 plus years, the majority of business, and I say that specifically, business applications have relied on storing something known as current state, right? What is the situation now? That's what I care about. And in order to process this, you process transactions, and then if you want to know things that had happened but were not recorded, you have to implement some kind of audit logging. A perfect example was Hibernate or Hibernate and VARs, where you can start to track things that you do inside of Hibernate. But the point of it is that you require extra coding to do this. It's not implicit inside of your model and how you process or reason about your environment. So, current state only, these types of models. This has not always been the case. I believe it's a side effect of RDBMS systems. Interestingly enough, internally they do not do that. High performance systems, mission critical systems, they do not store data in this fashion, relationally, if you will. I come from an energy industry. We use SCADA systems there. The SCADA historian is event source based and actually tracks just deltas. So if it has 2 or 3 readings that are identical, it doesn't actually persist that. The implied model is that if nothing has changed, then you can use the value that was recorded and last known. And file control audit systems, et cetera, back on the mainframe with vSAM data sets and such, keeping track of inserts and changes to files were tracked this way too. So the notion of event sourcing is actually quite old. So it provides a means by which I would say we can capture the real behavior, right? You're capturing behavior, historical behavior, and from that you can derive intent. Whereas if you're only capturing current state, you only know what the current intent is. You don't know what led up to it. You don't know the history, if you will. What's the saying? Those who do not know history are doomed to repeat themselves. So event sourcing is a way of achieving this. It's behavioral in nature in the sense that you're capturing events to whatever granularity that your business defines them. And it can be used in conjunction with the notion of commands, which we'll talk about, but essentially a command is something that comes in that can be converted into one or more events, and current state is never persisted. It's just an append-only sequence of events. Current state is derived. The nice thing about this is it gives you a very simple key structure. You don't need compound keys. You don't need complex keys. And as a result, it's much easier to distribute. Additionally, it can simplify the idea of trying to synchronize your data model with your business domain, right? We try to do that a lot where we have a database and we want the table structure to look just like the way we model our domain and so forth. In event sourcing, that's not the case. It gives you a much simpler approach. So commands, what are commands? Everybody knows what a command, anybody who has had parents knows what a command is, right? I issue them to my children and sometimes they abide and other times they don't, but it's to give an authoritative order. It's about behavior. I say to my daughter, clean your room, right? That's the command, clean your room. Or in this case, register client, client locale is changed. And the idea is we have this verb-noun format. The verb comes first and then the noun. And it's essentially a request to do a task or an action. They're imperative, and as such, they can be rejected. They're a request to mutate the state. Your room is currently not clean. I want you to mutate the state of your room to a clean state. And they transfer in the form of messages rather than data transfer objects as we think of. One could argue they're similar, but another thing that they imply is a task-based UI because you have this notion of eventual consistency, which we'll talk about shortly. As I had mentioned, they can be rejected. They're not to be looked at as editing data or data edits. They're really a request or a behavioral request to change data. And based on system design, they have a tendency not to expose the internal state of your system, whereas with a CRUD-based model, that can be an issue. Not always, but it can be. They can greatly simplify your repository layer, and as I had mentioned before, you can take a command and it can be split into multiple events. So what's an event? An event is a thing that happens, especially one of importance. More importantly, it's something that has happened. It's past tense. And as such, they're indicative, and they serve as an indication that something has occurred. They are immutable until we can invent a time machine. They're going to stay immutable. And they cannot be rejected when they are processed. And so they follow a noun-verb context. So in the previous example, we had register client and client locale, or change client locale. This is client registered or client locale changed, or in the event of my daughter, it would be, she'll come out and say, cleaned room. No, not actually, but that's the idea. They're atomic, right? So if you think about CRUD, create, read, update, and delete, it's kind of an interesting concept. It could be looked at as create and created, read and read, I guess. But the idea is the more atomic you make your events, the more intent or behavior you're capturing. And who decides that? The architect? He has an input or she has an input, but really the business has an input too. It's what's important for you to capture. So verb noun implies behavior, they're immutable. The beautiful, beautiful thing about events and event sourcing is they provide a natural verifiable audit log. And in the energy industry, security is very important. And everything must be audited. So it's really nice when you walk out the door with a system that is a natural audit log without having to implement anything. That's the way your system was designed. As such, they also cannot be rejected. So the canonical model of this is probably the easiest way to understand it, is a checkbook, an account register. You can see here a bank account register that has some debits and credits, ATM, check withdrawals, etc. And you'll see deltas there under the change column. And then to the right for an optimization, we have the balance that's calculated with the last known applied delta. And from an event source point of view, you would have your event store, and each one of those statements there would be an event that would be appended to the store, if you will. Now imagine a scenario if your bank didn't model their register this way, if they only stored current state. But you, however, you reconciled your bank account and you see an error. You say you have $10,000, they say you have $5,000. So you go in and you ask them a question and they say, well, Mr. Duncan, our account says you have $5,000. And I say, well, no, here's my registry. See, I recorded everything. And they say, we're sorry. We only record current state. So the last update was to decrease your balance to $5,000. We have no record of anything. You probably made a false entry into your register. I mean, that's ludicrous. Obviously, that would never work. So why is it only positioned for registries, things of importance? Why does it have to be that way? Well, it doesn't. It can be used pretty much for any model. This is just a rehash of what I said, but essentially you're going to persist each transaction as an independent event. You're going to calculate the balance or the delta of the current transaction, and you're going to apply it to derive your balance. It gives you a verifiable audit log that can be reconciled for validity and can be replayed, and you can derive current state at any point in the timeline. That has an interesting impact on analyzing intent by observing behavior over between time boundaries. As I had mentioned the last point there, and I believe that this allows you to derive or to study or to learn the real behavior of how your system is being used. So Akka Persistence. Akka Persistence is a library that is part of Akka. It provides the notion of something called a persistent actor, or a persistent actor model, which is a trait that you apply to your structure, and it will persist internal state. But it does more than just that. It also manages you'll see the last bullet there, identity or identity end state. So what is identity? Identity is who you are, or what you are, or what some domain object represents, where state is the sequence of events that got the identity to its current position, to where it is now. So Akka Persistence can provide both of those mechanisms for you, and it depends on to what point that you would like to take it. And we'll show some I'll show some examples here shortly. So the persistent actor is a stateful actor. It's thread safe just like all other actors. You have to work real hard to make it unthread safe, i.e. by exposing or leaking mutable state. It supports something known as command sourcing, as well as event sourcing. And I'll just talk briefly about command sourcing. Command sourcing is the notion of essentially persisting everything that comes in without validating it. This can be useful in transient debugging, right? But there's a cost, right? The number of messages, we'll call them, that you're persisting is increased, and you're also persisting errors in your system. When you replay, in theory, your system accounts for those errors, so your system's not broken, and it does allow you to track down errors by replaying history to that point of the error, and then you can see it. So it is a tool. I generally do not use it. I prefer to go with straight event sourcing, where I'm going to validate my commands and reject them if they're unacceptable. But you can do both, and a lot of times command sourcing is used for super high volume, where you're just going to persist everything, bam, 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 and deal with it later. In the model, implicitly, optimization for replay is built in, and you can recover from both your journal, which is the event store itself, or snapshots. So first, the journal. It's an append-only storage model. It controls, the application controls which messages and/or events get journaled. That's up to the programmer. It's pluggable. There's several journals out there in the community plugins, and the default journal is level DB, which writes to the local file system. Replicated ones can be found at the community plugins page. We also have snapshots, which again are primarily an optimization. You know what a snapshot is, right? It's an optimization. I don't want to replay my entire history. I'm going to replay it to the last known snapshot. I have the entire history if I need it, perhaps for some maybe big data grooming or what have you, but I can replay back to the last known snapshot, and recreate my internal state from that point and then replay the events from there on. There's a lot of journals. Some journals give you error. If the last known snapshot is corrupt for some reason, it'll roll back to the next known snapshot, what have you. So there's optimizations depending on the journal. But the snapshot implementation is also pluggable. The default one, again, uses level DB and writes to the local file system. So in Akka Persistence, the first thing we have here is the notion of something called receiveCommand. In traditional event sourcing, you have a command handler and you have an event handler. In Akka, they're kind of merged together with this partial function here, and you have two of them. First, the receive block, which is going to, at first, if you so desire to validate your command, in this example, it's going to fold over this function validate registration, and it's going to create a list of non-breaking error validations. It's going to return them as a single group. And then if it's a failure, it gives it back to the sender. Otherwise, it's going to call persist. In this case, that's synchronous, or persist async is the other option. And then we're going to side effect with inside that partial function. One key thing to note is that if you do use persist async, Akka will immediately process the next event. So any side effecting that occurs within that block, you have to account for in your state management aspect, because it's going to process super fast. So, and I'll show you what I mean here, I think, on the next slide. Yes, our identity and state. So in here we have an internal mechanism for capturing state. We have the evil var, right? But this is enclosed with inside the actor, so it's thread safe. And our state in and of itself is a case class, which is immutable. So we're doing defensive copying, essentially. So what we have here is kind of like an in-memory cache of current state. We don't have to hit disk if we want to know what the current state of now is. And this is not, I'm not talking about CQRS today, but essentially it gives you a really nice thing to have here. And then the recover is when you bootstrap the actor. It will then spin back up and it'll replay the events or replay the snapshots to bring it back to its current state. So this gives you resilience. If your actor crashes, the system will spin it up again and it'll recover where it was. You don't lose your data. A very powerful mechanism to reason about. So cluster sharding jumps into this. Identity is the notion, as I described. I have identity. I am Duncan, right? And as a result, or I am a human being. If I have a big system, if my house is too small, then I need to get multiple houses, right, for multiple people to live in a community. And that's the idea here. We can take that identity and we can distribute it across several nodes. Where one machine is not enough, it's resilient, it's elastic, it will activate and passivate messages. But the key thing, the powerful thing here is I don't need to know which house the person is in. I have something called a shard and a shard coordinator and a shard region that I can simply ask, person shard, where is Duncan? I don't have to have the path of the actor. I don't need any of that. And it'll manage all that for me. And surprisingly enough, it uses Akka Persistence under the covers. So shard region is on each node. It's an entry point, whichever node you come into when you ask your question. The shard region will either know where the actor is or it will ask the central coordinator for the first time only, and then it knows the path to traverse. If the actor does not exist, it will create it. If the actor, in other words, if it has passivated or has never been created, and there is a mechanism that you can apply. You don't want actors hanging out in memory if they're not being used, so they'll passivate and go away. But yet you don't lose your state, as we were showing earlier. So again, it's just explaining the shard coordinator and just keeping track of the time here. The first message comes in and gets resolved there. And from that point on, it goes to the target destination. So this is just an example of how you set up sharding with Akka, cluster sharding. There's some things that you need. You need an extractor and a resolver, etc. But it's pretty simple, and you can kind of think of it as a proxy. So when I send the command, which is change client name, I'm going to send it to the region. And the region is going to extract that first value, 123, the ID, out, and it will determine through the shard resolver where to send that message to the correct actor. So this brings us to one of the challenges behind this is consistency. Conformity in an application of something typically necessary for the sake of logic and accuracy, right? We want to be consistent across our distributed environment. In a monolithic system, they are trivially eventually consistent in that there is still eventual consistency, even though it might be at the microsecond level, but we take it for granted because we have a tightly coupled system and we a lot of times use a centralized database. Yeah. Okay. Let me bounce through this. Can I get 2 minutes? Okay. So strong consistency is an important part of that. The other aspect of it is in distributed systems, you lose that. And if you're familiar with CAP theorem, you have the 3 pieces of it: consistency, availability, and partition tolerance. You can't have all 3 at the same time. And that's this diagram here where the center, NA, is not achievable in distributed computing. So you have to deal with that. The reality of it, it comes down to eventual consistency. And the idea is that you're going to make the different nodes in your system eventually consistent as long as there's not a right in between. That eventually things will be consistent. And that's the way we live our lives. We're eventually consistent. Eventually the message gets there and we all see the same thing. So I'm going to stop there only because there's some other things. I'll be around for some questions if you have any, and we can do them offline because I want to give the next person time to get up here. But I appreciate you guys coming out, and I hope that if you're not familiar with this, that at least it'll give you something new to take a look at. And if you are, perhaps you can, you've learned something, or maybe you can come up and teach me something. So I appreciate it. Thank you very much for your time.